The second paper is titled Robust Training for Deepfake Detection Models Against Disruption-Induced Data Poisoning. The presenter is Park Jae-woo, who he is a graduate student at Yonsei University. Yeah. Let's begin. No, he's not ready yet. Okay.
Thank you. Hi, I'm Jeo Park from Yonsei University, and today I'm going to present robust training for deepfake detection models against disruption-induced data poisoning. This is co-work with my colleagues Hong-eun An, Rae-hyun Park, and my advisor professor Tae-kyung Kwon. Now I will start with the background. Deepfake is a combination of the words deep learning and fake, and refers to the use of deep learning methods to generate fake content. This is done by overwriting an existing image or video with a new one. As technology advances, it becomes increasingly difficult to determine whether an image is deepfaked by human eyes. This has led to a number of problems that exploit deepfake techniques. To solve this problem of deepfake abuse, there is a lot of research being done in two main areas: deepfake detector and deepfake disruption. The first way to prevent the side effect of deepfakes is by detecting deepfakes. Deepfake detection is a method for determining whether an image or video is a deepfake. A deep learning model, a deepfake detector, is trained using a large amount of data, deepfake images, and normal images to determine whether an image is a deepfake or not. In the video below, you can see the face X-ray detection method presented at 2020 CBPR, which is detecting the deepfake images. You can use this trained deepfake detector to find the deepfake images. The second way to prevent the side effect of deepfake is to disrupting deepfake generation. Deepfake disruption prevents deepfake generators from generating deepfake images by adding disrupting perturbation to image. In the image below, a disrupting perturbation is added to real image to create a disruptive image. When this image is input to the deepfake generator to generate a deepfake, a disrupted image is generated instead of deepfake image. Here we have one question. Can the two defense methods coexist? The two methods described above for preventing the negative effect of deepfakes take two very different approaches. The research for this paper started with one question of what happens when two completely different defense methods coexist. The deepfake detection model is trained by the real images and the deepfake images. Training a deepfake detection model requires a large amount of data, so it is necessary to create dataset by collecting data from the internet as well as using existing datasets. Meanwhile, deepfake disruption prevents proper deepfake creation by disrupting deepfake generation. Before uploading their images to the internet, people will add disruptive perturbation to their images to prevent them from being used in deepfakes. Let's consider a situation where both defense techniques coexist. As I said before, people will add disrupting perturbation to their image and upload them to the internet. If a disrupting perturbation is added to the data that was collected to train the deepfake detection model, it can poison the deepfake detection model, so preventing it from learning correct deepfake data information. As you can see the blue-colored procedure in the image here, which is a normal training procedure, deepfake images are generated where, as you can see, when they are generated with the real images. The deepfake detection model trained it with these images will show good decision boundary and high accuracy. However, If you see the red color flow in the figure at the bottom side, which is an erroneous training procedure, a disruptive image will be used to generate disrupted images. And the deepfake detection model trained on the disrupted images will show the bad decision boundaries, as you can see in the picture. This caused the detection rate to drop. To examine co-expanding problem, we conducted motivation experiments. We can see that the difference in accuracy between the detection models trained with disrupted images and the detection model trained with a clean dataset is significantly different. In the graph below, you can see the detection performance dropped almost half. So the answer to the question, can the two defenses coexist, is temporarily two defenses cannot coexist. So I'm going to talk about our method to solve coexisting problem. After connecting the data trained the deepfake detection model, we can use purification to remove the disrupting perturbations to generate a proper deepfake image. Key idea is to remove the disrupting perturbation at the detector training level. So you might be wondering how we are going to purify the perturbation. We are going to use a diffusion model for purification. Diffusion model is a method of generating an image from noise using a diffusion process. In the figure on the left, the image of x0 is transformed into the noise of xt through the forward diffusion process. The diffusion model is a model that reverses this forward process and generates an image from noise through the reverse diffusion process. By using this model to generate an image from noise, we are able to remove the disrupting perturbation. So hasn't there been any work on removing perturbation using diffusion models? This year, a paper on removing adversarial perturbation using diffusion models was presented at the 2022 ICMR. This year included the forward process to add noise and the reverse process to remove adversarial perturbations together with the added noise. However, if noise is added through the forward process, more changes are made in original image and more time is required for purification. Our proposed method is to remove only the disrupting perturbation through the reverse process by removing the forward process. This minimizes the deformation and reduces the time taken for purification by 7.75%. Our proposed framework for training a robust deepfake detection model is as follows. We will explain the steps in orders. The yellow marking in the figure will help you understand. First, we collect the data for training the detection model. In typical training phase, you generate the fake image directly from the data you collected. However, in our framework, after gathering dataset, we address any potential disrupting perturbation using the diffusion model. It worth noting that the diffusion model employed for this purpose is based on the denoising diffusion probabilistic models introduced at URIPS in 2020. Next, we create a deepfake image through token using our previously purified real images. We use the generated deepfake images and real images to build a training dataset for the detection model. This dataset can be used to train a deepfake detection model. Now, let's take a look at the evaluation of our method. Here's the environment we ran on our experiments in. We ran our experiments on Ubuntu 20.04 and used a machine with 2 NVIDIA RTX 4090. The deep learning library we used was PyTorch 2.0. The target deepfake generation model was Togen, which was released in 2018 CVPR. Before the experiment, we present 2 research questions. The first is about purification performance. We've tried to find out does the deepfake generate well after the purification is applied. The second is about accuracy preservation. Here, we want to check can our purification uphold the accuracy of the deepfake detector. Firstly, let's delve into the experimental research regarding purification quality. We found similar defense performance to existing method. For L2 distance, we can see that our method performs similar to existing mitigation techniques and is below the disruption threshold of 0.05. Also, we can see that FID also performs similarly to traditional defenses. In summary, we can see that our method is able to generate deepfake images well below the threshold of disruption criterion. It also shows similar defense performance to existing defense models. The answer to research question 1 is yes, deepfake generated well. But based on this research alone, it is difficult to see how our method is better than existing defenses. Let's look at the distribution of the purified image. The blue mark in the distribution, like this, is the distribution of the disrupted images or the images with accuracy defenses applied it. Yellow mark in the distribution of deepfake images, and the green mark is the distribution of the real images. If you look at the bottom left here, you can see that the distribution of the images purified with differ is different from the distribution of the deepfake images. On the other hand, we can see that the images purified with our method have an image distribution that is almost identical to the deepfake images. Next, let's see if we did a good job of creating a deepfake of the purified image. You can see that each row of an image, it has been changed to the black hair, brown hair, and man. Each column shows the original image, deepfake image, disrupted image, and purified image. You can see that the disrupted image does not generate a deepfake well due to the addition of a lot of black color, while the purified image generates a deepfake well. Second, we show the experimental result about accuracy preservation. Looking at the exception model and the ResNet 80 model, the existing defense performs similar to the unprotected model, but our defense have only a small drop in detection rate compared with no attack. The ResNet 50 model also performs well against differ with 73 to 85%. However, our defense techniques show 90 to 96%, which is much better than differ. In summary, we show that the detection model trained on the deepfake dataset using our method outperforms the existing defense by 11.27 percentage point to 45.72 percentage point. Therefore, the answers to research question 2 is yes, our purification uphold the accuracy with training with disrupting images. In conclusion, we present for the first time to address the problem that can arise when deepfake disruption techniques and detection model techniques coexist. We show that our method is more similar in distribution to original deepfake dataset than existing defenses. We also show that detection model trained on the purified data with our method outperform detection model trained with existing techniques by 11.27 percentage point to 45.72 percentage point. Finally, we hope that our detection model training framework can be used to train robust deepfake detection models, which will help prevent the harm of deepfakes. This is the end of our presentation. Please feel free to ask if you have any questions or send us emails. Thank you.